Hello again and welcome to this video. In this video, we're going to continue on our natural language processing series. Now, before moving forward, we need to understand through some concepts here. So the first concept that I'd like to introduce is theory of automata. Theory of automata is the study of abstract machines and the computation problem that can be solved using these machines. This abstract machine is called the automata. Now, automation consists of states and transitions. When you try to understand state and transitions, we can take a very simple example of retrieving our money through ATM card. Example, retrieving money through ATM. So what do? We are at an empty state at first. We go towards the ATM machine, we do some action or we do some transition, go towards our ATM machine. After that, we insert our card. After that, the ATM recognizes our card and asks for our PIN number. We then provide our PIN number. If our PIN number is correct, then ATM asks us what to do. But if our PIN number is incorrect, we're again in the same state here. So if our PIN number is correct, ATM asks us many options like saving, withdrawal, or things like that. If we choose withdrawal, ATM basically asks you the amount. At this point, you can also enter the amount, after which the ATM provides you money, or at this point you can also choose to cancel your operation, which goes to some other state. Cancel your operation, and yeah, you move on like this. So the round circles that you see here are your states, and these arrow lines that you see here are the transitions that you make upon doing some kind of action. Okay, so there are some few terminologies that you need to understand whenever you're talking about theory of automata. The first one I'd like to introduce is symbols. So symbols are entities or individual objects which can be any letter, alphabet, or any kind of picture. So if I say in very plain terms, symbols can be a single letter, alphabets, symbols, or maybe anything. Okay, so these are symbols. They are just entities or individual objects, nothing more. The second concept is alphabets. So whenever we're talking about alphabets are a finite set of symbols denoted by epsilon. So alphabets are basically denoted by epsilon. Okay, so these are collection of symbols. So if I say A, B, C, D, now A, B, C, D are alphabets, and my A or B or C or D is a symbol. This can be in any form. Let me just write 1, 2, A, B. Okay, this can be in any form. So they are just a collection of symbols denoted by the epsilon. The third concept that I want to introduce here are strings. So strings, they're basically a finite collection of symbols from the alphabet. So string is denoted by W. For example, if set of A and B are alphabets, various strings that can be formed from set A and B are A or A, like A, B, B, A, B, and things like that. Okay, so it can go up to infinite number of strings that can be formed here. A string with zero occurrence is known as an empty string. Okay, so this basically contains nothing. It It contains 0 symbols and is denoted by the symbol. And a number of symbols in a string is called the length of string. So when we talk about the length of string, it is denoted by this symbol, and this is the number of symbols present in the string. So if I say AAAB, a string AAAB, the cardinality or the length of the string is 4 here, as there are 4 symbols in the string. Another concept I'd like to talk about is language. Language actually is a collection of appropriate strings. A language which is formed over a set of alphabet can be finite or infinite. So for example, if I say a language 1 is a set of string of length 2, then it can be, if my alphabet set are A and B, so these can be AA, AB, BA and BB. Okay, we cannot make any more string of length 2 here. So this is also called finite language. But when we look at another example, like say set of string that starts with A, but for this one there can be infinite number of strings, string formation here, which can be A or A or ABB or ABA and so on. Okay, there's no such end to such strings, and we call this as an infinite language. What does finite state automata do? Finite state automata are used to recognize patterns. Finite state automata takes input symbol and changes its state accordingly. When desired symbol is found, transition occurs. At the time of transition, automata can either move to its next state or stay in the same state, like I said. And finite state automata has basically 2 states. One is accept and the other is reject. So state when the input string is processed successfully, it's called an accept. And in case of accept state, the automata reaches its final state and then the process is done. Going any further, I'd like to introduce you with a concept called context-free grammar, or I've indicated this term even in my previous video. Well, my previous video is all about introduction in natural language processing. If you haven't seen that video, please go to the link. I'll keep a link above so that you can go and check it out and then come back here so that you'll understand the video concepts more properly. So what is the context-free grammar? So a formal definition of context-free grammar is that it is a finite automata which is a collection of 5 tuples. So those 5 tuples are Q, summation, delta, Q naught and F. Now what do each of these symbols denote? Q basically denotes your finite set of states. Remember, finite set of states can be infinite here. Summation denotes your finite set of input symbol, again has to be finite set of input symbol. Q naught is my initial state. F is my final state, and these delta knots are transitions from one state to the other. We can also call them transition function. So we basically have 2 types of finite state automata. One is deterministic finite state automata, and the other is non-deterministic. In DFA, the machine goes to one state only for a particular input character. and DFA does not accept a null move. So if I give an example of DFA, if I say my alphabet collections are 0 and 1, and if my language accepts all strings starting with 1, then so if I have to construct a DFA here, my Q0 is my initial state. If an input of 1 is given, then I go to my final state, which is denoted in this way, and then any term that happens here can we can just stay on Q1 because the alphabet basically starts from 1, and then the Q1 is my accepted state. But if I get another input 0, then my transition goes to Q2, which is not a final state. So yeah, for one input there is only one action here in case of DFA. So in DFA, the input to the automation can be any string. Now we put a pointer to the start state Q0 and read the input string W from left to right and move the pointer according to the transition function. Okay, the other is non-deterministic finite automata, which is also called NFA. NFA is used to transit any number of states for a particular input, and it can even accept a null move. Okay, when I say my alphabet collections are 0 and 1, and my language accepts all string starting with 1. So if I build an NFA here, what I can do is I'm at Q0, I give 1, I reach Q1, which is my final state, and like if I give any other numbers, I stay at Q1. But in case of DFA, I had to define what the input 0 does here, but in case of NFA, it's not compulsory for me to define what the input 0 does here. We'll try one more example of DFA here. We have to design a DFA with alphabet A and B that accepts even number of A and even number of B. So how do we make this diagram? We basically need an initial state here. So Q0, if we get an A, let's go to Q1, it's not a final state. If we get a B, let's go to Q2, again not a final state because it has to be even number of A and B. So from here, if I get a B here, I go to Q2 again, which is not the even number of A and B because I just have one A and one B. But if I get another A here and another B here, okay, also denote the arrow because this will be confusing later on while trying to understand it. So if I have one A, one B, one A and one B, so the total number of A are 2 and the total number of B are 2, which means this can be our final state. Again, if I have one B, one A, another B and another A, again this can be our final state, accepting even number of A and B here. No matter how many number of A and B you add, it's not going to be wrong. Okay, so this is all for this video. In this video we discussed about theory of automata and various terminologies used in it, and then we also understood DFA and NFA. In the upcoming video we're going to talk about regular expressions. So see you in the next video.